Hello everybody and welcome. Yes, we are back to making niche communication protocol videos. So congratulations I guess, you clicked the link, welcome to the club. Today we are looking at controlling this LS-M100 VFD over Modbus. I'm going to be doing it from this Siemens PLC, but you can use anything you want that can act as a Modbus master. Yes, this will be specific to the M100, but I'm going to explain it so that you can use it on any other VFD, as they're all mostly set up the same, just using the same 3 cardinal settings. So without much further ado, let's look at how we get this VFD walking and talking in Modbus. First order of business is to hop on over to the datasheet. If you didn't get one with the unit itself, usually Googling the make and model will get you all of the information that you need. I've put a link in the description to the make and model I'm using if you're actually running the same kit. Anyway, for this VFD, or indeed any VFD, we just need to change the same 3 cardinal things. And that is the command source, i.e. what is telling the VFD to turn on, turn off, running in reverse. And 2, the frequency source, like what is telling the VFD how fast to turn. And 3, actually configuring those communication settings. So if we go to the table of contents, we can see here in section 5.1, setting the frequency reference. So that is one of our things we need to change. And the second is here, setting the command source. And the third, if we go down a couple of pages, is here. So inside of RS-485, setting the communication parameters. So let's have a go at changing all of those. Out of the box, 9 times out of 10, a VFD will be configured to just work with its own buttons. So you can see if I change its frequency on that dial, if I press run, it'll ramp up to that speed. I can change it. This little light here means it's running forward. If I turn it off, it'll ramp down. Lovely stuff. So if we go into the datasheet and we have a look at the command source configuration, we need to find DRV. So if we come up on the options, that says DRV apparently. If we go into here, press enter, this is currently set to 0. According to the datasheet, we want to change this so it's listening to RS-485 communications. So we need to change this to a 3. Press enter on him a couple of times. And that is DRV set. And we can check that by going back into DRV and it's still set at 3. And the next setting that we need to change, if we have a look in the datasheet, is the frequency reference, and that is FRQ. So if we move up to FRQ, there he is, go into him. And we're currently on 2, which makes sense because we're using the knob that's inbuilt into there, the 0 to 5 volt little potentiometer. We need to change this up to 9. 9, press enter a couple of times, and then we'll check that that's actually set at 9. Yep, good. So we have set the frequency and we have set the command. What we need to do now is set up the communication protocol. So let's come back to the main menu, if you will, all the zeros. First thing we can see is now none of these buttons are working, which is good because we've told it only to listen to RS-485, not listen to these buttons. So that is exactly what we want. But we need to actually tell it to listen properly over RS-485. Now, this isn't for every VFD, but some VFDs do this. If I press this mode now to go into the advanced mode, it won't work. I need to tell it to let me into that advanced menu. This will be different on different VFDs, but if you come along on an M100 until you find, where is he? OGR, you need to set OGR to true. It's either true or false to let you in. So it's currently set at 0. We want to set it to 1. So we'll check that OGR is actually at 1. Yeah, good. And now, once we're out of OGR, back in the main menu, we can come into, look at that whole new advanced menu for us. And what we want is the CM. And in VFD numbers and letters, that is an M. Go figure. So the way this CM works is there's a bunch of codes for the CM. We're on 0 at the moment, which is nothing. As we go up through the codes, we can change different criteria about our communication settings. So if we go to CM1, that should be, according to the datasheet, the actual inverter address. So this is our Modbus address. So if I go in here, you can see I've already set this to 10. So this VFD is sat at address 10. CM2 should be the protocol selection. So this is where it gets a bit weird because you can do straight up Modbus on this, or you can do LS's own proprietary communication protocol, which you'd set a 1 for this. This is set at 0 because we don't mess about with any of that nonsense. So keep that as 0. CM3 should be 3, yeah, for 9600 baud rate. CM4 should be set as 0 for having 8 data bits, no parity, and 1 stop bit. So yeah, this is all just the normal industrial standards. And CM5 is 5, which is a 5 millisecond timeout. So that's all of our settings done nice and easily. And we can come back out of that CM menu, cycling through back to here. And now the VFD is technically all set up for Modbus. It's not listening to anything from the pot. It's not listening to any of the buttons. So that's a good start. Let's have a look at how to actually wire this thing up now. So how do we get this old girl wired up? We've come down to the RS485 communication part of the manual, and going through, it all looks very, very normal. There's nothing that jumps out and says anything is weird or different, apart from this installation type bar. We're on an RJ45 connector. So your VFD might just be a couple of terminals that you put the data wires in. Here, it has to go through an RJ45. So let's have a look at what that looks like on the VFD. And lo and behold, it is true. It is on an RJ45. So if we pull this guy out. So I've crimped this guy up to the T568B wire pattern on this end, and I've just left the wires exposed on the other side just to clip into some of the stuff that I've got going into my CB1241 module. But yeah, this is an RJ45. It's not super common going into these, but it does happen. It's nothing to lose your mind over. So let's have a look at this in a bit more depth. This is on an RJ45. And this is specifying that pin 1 is signal positive, pin 8 signal negative, and pin 7 is signal ground. So on the next page, there's a bit of a zoom in. So here's our RJ45 connector. Here we can see we have pin 1, pin 7, pin 8, signal positive, signal negative, and signal ground. And if we compare this to a T568B pinout, you can see that our pin 1 should be orange and white, our signal negative on pin 8 should be brown, and our signal ground is going to be brown and white. So that's how I've crimped up my my RJ45 connector. And of course, if you want to know how to wire this up into the CB1241 port of the PLC, I'm going to pop a link in the top of the video now for you to have a look at another of my videos where we go into that in much more depth. So now we've got the VFD configured, we've got it all wired up, let's get to some programming. Okie dokie. So we're in a brand new script. Nothing in here yet. I'm going to go pop the PLC in and start throwing together a framework very similar to the last thing I did on Modbus. And then we'll jump back in and start doing some actual VFD relevant stuff. So cue some jazz. Okay, so now we have set up our standard Modbus communication, very similar to the last video. Only difference is I have popped the Comm load into a startup block, so that just runs once on startup. It sets us up exactly the same, so using the CB port, 9600 baud, no parity, blah, 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 and linking to the master at DB2. In the main, very similar stuff. I've also set us up a database called Modbus Config. Inside of here, we have a bunch of holders just for, you know, is it done? Is it busy? Blah, 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 blah. And I've wrapped this background. So basically this is requesting every time it's not busy. If you're building this into another system, probably a better idea to do that in a more constructive way. This will just run as fast as humanly possible because we're just addressing this one thing at this one address. So what do we do now? We need to pop in the rest of the information in this config file. What do we know? We don't know too much right now. We know the Modbus address because we set that. So let's pop that in as 10. Everything else, the data length, the data address, we don't know that yet. So let's go back to the datasheet and work it all out. So this is the compatible common area parameter. Generally, this is known as a Modbus map or a Modbus register or a register map or combinations thereof. And this tells you what is where in the memory of the VFD. Now, this can throw you a bit because from coming into this fresh and just looking at it, you would expect, this is hexadecimal 0001. You'd expect this to be an input coil because it's around the low end. This is the case with this. I've used this VFD before, I know it. You just have to have a play. Sometimes they are not, sometimes it is legit, the input coils or something like that. This is all assuming an offset of 40,000 in this. So where you see hexadecimal 0001, it actually means 40,001 offset. And this is a big old list of everything in the VFD that you can find out, read or write over Modbus. So this is incredibly useful to us. So for example, because I can only read this memory address, if I read 40,001, it will tell me back what the capacity of the unit itself is. That's all well and good, but it's not what we need now. What we need is the two things that we set up on the VFD at the start of this video, which is the frequency, which is this guy, and the operation command, which is this guy. In a very nice twist, they are both sat together. So we have address 5 and address 6, which in reality is 40,005 and 40,006. So we immediately know, because these are the only two things we need, our data length is 2, because we can just do it in one operation. We can do one write and write to this and to this. So we can nip back into the portal. So we can put our data length as 2. And the data address is the starting address of those two things. I'm all over the place. So the starting address, like I say, 40,005. Fantastic. So we know we're writing to these two addresses, and we're starting at address 40,005 with the second one being 40,006. So what are we writing into those? Well, the first one is fairly obvious. It's just the frequency. One thing to note is this multiplier here. We can only send integers over Modbus, well, in this incarnation anyway. So if we wanted to, say, for example, put a frequency of 12.34 Hertz, we would actually put the integer 1234, and inside the VFD that is going to get divided by 100 to give us 12.34. But that's the only thing, we just put it in as an integer, it gets divided by 100, easy done. So generally we're going to be running this up to 60 Hertz, so we will be telling it 6,000 and that will get divided through to 60. The operation command goes a bit more binary. I don't really want to go down the rabbit hole of binary in this video, but it is effectively a 16-bit number that is sent over. So there is 16 bits. Each bit corresponds to something different. So B0, the very first bit, if that is high, you will issue a stop command. If the second bit is high, you'll be running it forward, and so on and so forth. We're only really interested in these first three for this video. So stop, forward, and reverse. If we set the fourth bit, that would reset any faults that we had. If we reset the fifth bit, or confusingly called B4 here, that's our e-stop if we wanted to issue an e-stop. One note, doing e-stops with VFDs, very dangerous. Only do them in an actual emergency, especially if you have stuff hooked up to it, especially if you don't have a braking resistor. If you do an e-stop when you're running a big inductive load like a fan or something, it's a very, very quick way to atomize your VFD. So that's just something to bear in mind. So don't mess around with this unless you linked up your braking resistors and you've done all your calculations for your energy dissipation. But like I say, we're only going to be concerned with these first three bits. The bit after e-stop is reserved, so we don't need to worry about that. And the bits after are more just feedback for other stuff. These are read-only, just lets you know different states of the VFD and what it's doing. And the last three bits are all reserved as well. So not wanting to go too far down the rabbit hole, in very, very simple binary terms, the first bit, that's your ones column effectively. So if we send the integer 1 to this memory address here, 40,006, that will tell the VFD to stop. If we want to run it forward, that bit pattern would be 0, 1, 0, 0, 0, 0, 0, 0, 0 going on, and 0, 1, 0 is 2, because this is your 1s, these are your 2s, and these are your 4s. So if we send the integer 2, we will run it forward. If we send the integer 4, i.e. 0, 0, 1, 0, 0, 0, 0, 0, blah, 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 that will be reverse. And that is how we control this. You'll find these this bitwise thing quite often in these VFDs because it's a very good way to pass information around. So if we just come down into more of the readable stuff further on in the memory, you can see at hex address E, or 40,000 and E. I'm mixing it all up, but you get the idea. This is where our operation status is. So we read all of these bits, and by looking at which bits are 1 and which bits are 0, we can work out what the VFD is doing. Is it stopped? Is it operating forward? Is it operating in reverse? Is there a fault? Is it currently accelerating, decelerating? All of these very useful things that you can use to gain information on what is the VFD currently doing, and generally the same thing with fault information. When you get a fault code, it's going to be 1001100, just telling you what's blown up, what's gone on. So when you start building this into bigger programs, this is a really good way of not just knowing you have a problem, but knowing exactly what that problem is, and maybe sending automatic emails to people to get to site and fix stuff, all of that good stuff. But definitely out of the scope of this video, but that is how these bit pattern things work. We only need to work with the first three bits, which is effectively in decimal 1, 2, and 4. So let's go and do something with that now. All right, so back in our main, we are going to put down a couple of switches. So I've still got my switch array hooked up from my other tutorial videos. That's not a plug, but it is. Go and watch them. So I'm going to put a switch 1 here. And what I want switch 1 to do is basically run us in forward operating mode. And if you remember from this, our forward operating mode is the second bit. So it's not 1, it is 2. So when we have switch 1 on, we want to send a 2 to this memory location. We're not going to send it exactly there yet, but we're going to put it in somewhere that will get sent there. So switch 1, we want to move a 2 into this VFD command place in our PLC memory. So this is nothing to do with the VFD yet, this is just letting us manage our memory. And when we want switch, when we switch 2, we want the VFD to operate in reverse, which is 4. So we're going to do exactly the same thing. For that. Now, the eagle-eyed among you will have spotted an immediate problem, because if we have switch 1 and switch 2 on at the same time, we're going to get a race condition. That should not be the case when you're actually doing this in the real world. I'm just building a very quick demonstration to show you, but yeah, definitely put more logic into it than this. This has lots of issues. And what we also want to do is when switch 1 and switch 2 aren't open, so these guys, we want to give a 0 into this same memory location. Nice. And thinking about it, just to tidy it up a bit, I'm going to put these all in one network. And in another network, we're going to work on our speed. So again, this is not the best way to do it. This is just for a very quick switch operated way to mess around with this VFD. I'm just going to want switch 3 and switch 4. When I bump switch 3, I want it to increase the hertz by, let's say 10 hertz. And when I bump switch 4, I want it to decrease the hertz by 10. So I'm just going to throw that together nice and quick now. All right. So all I've done is I've rigged switch 3 and switch 4 up just to a positive trigger. So when we switch it, it's going to, if it's not over the upper limit already, it's going to add on 1000, which is effectively 10 hertz, because remember we're dividing through by 100, and that just gets modified for the VFD speed. And then the same thing with switch 4, but we're just minusing 10 hertz from the same thing if the speed is not, well, above 0. If you send a number above 6000 or below 0 to the VFD, it just won't accept it and it won't do anything. So you're not going to break anything, but it's good practice to modify the stuff and sanity check it before you send it out. So the only thing we need to do is add a move block in here, because these are just memory locations in the PLC. We want to send this to the correct place in the array to get sent out to the VFD. So we know from this table, the first thing in our, because we're sending the data length of 2, so the first thing out in our array needs to be the frequency, and the second thing in our array needs to be the operation command. So let's just quickly do that now, and then we're all good to go. Done. Oh, I should also say as well, to make it all pretty, I've hooked up some lights. So when we're running forward, the first light is on, and when we're running in reverse, the second light is on. So again, like Christmas. So now we're all set up. Let's upload this to the PLC and start having a play. All right, so that's all on the PLC. Everything seems to be okay. Let's go online and see how we are diddling. All right, so no errors coming up on the Modbus, so that's always good. And we can see Modbus address 10, that's good. And the data address going in is 40,005, good. Data length 2, yeah, all good. And if we look on the actual PLC itself, because this is, like I say, this is just cycling as fast as it possibly can. You can see these TXRX lights on the Modbus module itself are just going hell for leather. So that's good. So we're moving 0 into the command, which is good. And the hertz is all 0 as well. And if we look at the VFD, this is what we're seeing. So we're at 0. Nothing we do on the front can actually change anything. Yep. But if we come to these switches, we should be able to start influencing stuff. So if we put it into run, we can see this, when it's not running, this VFD gives the hertz that it will run when it does run, if that makes any sense. I'll just do it, I'll show you. So this is saying 0, so when I run it, it will run, but at 0 hertz. So we can see our run light is on, and our run indication LEDs are on, but it's at 0 hertz, so it's effectively doing nothing. And we can try the same with reverse. So if this switch 1 goes off, you can see we lose those run lights, this light goes off, and now we're in reverse, our reverse lights are on, but still at 0 hertz. So let's try bumping up this hertz. If I go to switch 3 and bump it up, that is 10 hertz, 20 hertz, 30 hertz, 40, 50, that seems to work. And we can bring it down with switch 4. That is lovely. It's kind of like I know what I'm doing. So now we're at 60 hertz, but we're not running. You know, lights are on and we've got none of these running LEDs. If I pop up switch 1, you can see it just doesn't jump to 60 hertz. This will increase with the acceleration time that's been previously set inside of this VFD. So you're not going to burn out any massively inductive loads. So that's fantastic. So we can see our run light is on and we are running forward at 60 hertz. Now if I turn this off, we should come back down to 0. Now that hertz, it doesn't matter. It's not 60 hertz forward or backwards, it's both. So now we're back at 0, you can see we're at 60. If I flick switch 2, we're mounting up the hertz, but we're now in reverse, not forward. You can see our blue reverse light is on. Lovely stuff. And even as it's running, if I wanted to change the hertz, so we're at 60 hertz in reverse now, if I just blip switch 4, we actually bring that down by 10 hertz and another 10 hertz. Lovely stuff. And we can actually bring this down to 0 using these switches. So it would be stopped, but we are effectively still in reverse because we're still sending that number 4 into the operations part of memory. So we can stop that by changing switch 2 to off. So thank you very much for watching. I hope this video helped. If you'd like to see any other subjects covered by me, just let me know in the comments. Until then, I'll see you in the next video.